Here's the doozy of the proof. If the limit as x goes to infinity of f of x is L, and the limit as x goes to infinity of g of x is M, then the limit as x goes to infinity of the product of f and g is the product of the limits. And like always, these proofs are done by definition. I don't need anything more than definition than a bag full of tricks. So let us see what this means. The limit as x goes to infinity of f of x equals L. Now that's given. This is if and only if given any epsilon greater than 0. There does exist an N1 such that the difference between f of x and L is less than epsilon whenever x is bigger than N1. Okay, so we have that. Now, what does this mean? Oh, it means exactly the same. Just the letters change. The limit as x goes to infinity of g of x equals m. That's given. So that means given any epsilon greater than 0, it does exist in S2, N2, such that the difference between g and m is very small whenever x is sufficiently large. Now, I will say choose the max. Sorry. I would say let n equals the max of n1 and n2. And then I'd write down what's in blue again, except I would just write down n. I'd write down what's in purple, and then just write down that x needs to be bigger than n. Okay, but again, I'm not going to do that. But on an exam or you're writing down the proof, you should do it. Okay, now I would like somehow to get f of x, g of x minus Lm very small. Okay, so this is what we want. We want given epsilon greater than 0 that there does exist in N3. We don't know that it exists yet. We do not know that it exists. Given, but we want it to exist. So let's assume for right now it exists. And then hopefully later we can find it. Given epsilon greater than 0, there exists an N3 such that f of x, g of x minus Lm, let's start that over, such that f of x times g of x minus Lm is less than epsilon whenever this unknown, whenever x is greater than this unknown value. We do not know it. If we can find it, we got it. Okay. So let's look at this. Let us look at f of x, g of x minus lf. We need to be clever. So what I'm going to do is I'm going to add and subtract some things in here. This is the same as f of x, g of x. And then I will take away, let me think, I will take away f of x m, and then I'll add back f of x m. Well, of course, that's 0. And then I take away my ln. And there's a reason I did this, because when I factor out in there the f of x, I am left with g of x minus m. And then plus, surprise this plus. Okay. When I factor out the m from here, I get f of x minus m. Now, this is less than, since there's a sum here, it's less than the absolute value of this plus the absolute value of that, less than or equal. But the absolute value of that product is the absolute value of the first factor times the absolute value of the second factor plus the absolute value of m times the absolute value of f of x minus l. And now, some of this stuff I know. This is less than, strictly less than, the absolute value of f of x times, well, g of x minus m. Ooh, look at that. I know it's less than epsilon whenever x is bigger than n. So, epsilon plus the absolute value of m times f of x minus l. But I know as well, that's less than, this here is less than epsilon whenever x is bigger than n. Ooh. Whenever x is bigger than capital N. Now, if I can only find a bound on f of x. Now, I could have found it earlier, but I want you to see where we need it. So now, we need to kind of leave from here and do something else for a moment. We know that f of x is equal to f of x minus L plus L. So the absolute values follow. And this is equal to the absolute value of this plus is less than or equal to the absolute value of f of x minus L plus the absolute value of L. But now, this is less than epsilon plus L. But it's less than epsilon whenever x is bigger than n. Okay? This is less than epsilon only when x is bigger than n. Okay? So, f of x, this is less than that. It's less than epsilon plus the absolute value of L whenever n is bigger than capital N. Okay. Now, continuing from here, this is less than, Well, f of x we just learned, and we're only talking about when x is bigger than n. Ooh, f of x, something's a little bit wrong. The absolute value of f of x is less than epsilon plus L. Okay, now, let's see. Like I said, that's less than epsilon plus L. So we have less than epsilon plus the absolute value of L times epsilon plus the absolute value of M plus epsilon. And this is whenever x is bigger than n. But let's just remember that way up here we have this. This here is less than this whenever x is bigger than n. Okay. Now, if this epsilon was in here, we'd be in good shape. So you know what? I am going to choose that epsilon is equal to the min, epsilon prime, is going to be equal to the min of epsilon and 1. Now, let us see if we can understand what's going on. If epsilon is bigger than 1, then epsilon prime will be 1. If epsilon, these epsilons, if these epsilons are less than 1, then epsilon prime will be epsilon. Ooh, that means this has to be less than 1, or less than or equal to 1. Okay, so this here is less than or equal to that epsilon, the nasty one. I'm going to make it as big as possible. I'm going to make it 1 plus the absolute value of L times epsilon. But now epsilon, we're going to use epsilon prime plus M times epsilon prime. The min of those two. If epsilon is less than 1, then epsilon prime is epsilon. Okay, this is true whenever x is bigger than n. Okay, now this is equal to epsilon prime. I'm factoring out the epsilon prime. It's this that goes in the brackets plus that. Okay, now we are going to choose another epsilon double prime. And epsilon double prime is going to equal to epsilon we're going to say, well, I just have to think for a moment. We definitely want this. I don't know why this is bothering me. Okay. So, if I define epsilon prime to be epsilon double prime over 1 plus, okay, because it's for any epsilon, okay? So then I have that this is equal to epsilon prime, which is what I'm writing, times that 1 plus L plus M. And this cancels out, and we get epsilon double prime whenever x is bigger than n. Okay, so let us go back to what we have. We have this, which is equal to this, which is equal to this, which is less than or equal to this, which is less than this, which is less than this, which is less than this, which equals this, which is equal to this, which is equal to this. That is f of x times g of x minus Lm. Let's write it down neatly, please. Minus Lm. This here is less than epsilon prime whenever x is bigger than n. Okay, so we don't have to go back because all I said is in here was we want, but we found it. N3 should be n. Okay. Okay. Well, this is the same statement. This is the same statement as the limit as x goes to infinity of f of x, g of x equaling Lm. Okay, and this is just what we wanted to prove, and it was just playing games, making everything work out. I guess you may think it was more than this, but I think the key thing was adding that 0. That way I had an f of x common, and I was able to factor out g minus m. And it turned out on the other end I can factor out an m, and I'd have f minus l. Things that I really wanted, because I know what g of x minus m is less than. I know what f of x minus l is less than. F of x, we figured that out down here, right smack in the middle of the proof. But it's true. Okay, continue watching these videos, learn how to do proofs, learn how to think about these things.